Okay, welcome to day 16 of UTME and SSE preparatory class. We are in the topic of electric charge and electric field, which is the part 1 of electrostatics. This video concept covers maximum in-depth of knowledge in minimum possible time. I am actually here doing this live at you from Muzi Academy Studio with my students around me. They are looking at me and I'm laughing. So guys, I might be smiling in this video. Just know that what they are around me, they are the one behind my smile. So we start with the first one. The first question, an ebonite rod is rubbed with four. Attract a glass rod rubbed with silk because dash. Now, the concept about this, which you just need to know, like I told you, maximum in-depth of knowledge in minimum possible time. That is the essence of these video lessons. And to understand this, we talk about static electricity. Now, if you talk about static by static electricity by friction, you just need to understand that when we talk about static electricity by friction, which is friction method, one body must always be insulated. One body must be insulated. Like I said, I'm not going to talk too much. I'll only focus on what is needed. So what we do is that when we want to what electrostatic by friction method, one particular body must be an insulator. So the transfer of charges is always by, for example, the basic concept, you have a metal sphere, or let's say you have an iron rod. Drawing is always the problem. You have a rod on top of what? Of a cloth. Or you said a sick cloth. So if you are taking a rod which is positively charged with a cloth, which is generally a sick cloth. So when you actually place the rod very close to a sick cloth, the positive charge in this will be transferred to this particular body. So charges are generally produced by rubbing. When I say rubbing, Rubbing. So the experiment was actually performed by a man called Jupeb. I don't want to go into details because you guys are ordinary level students and I'm only focusing on what is going to be asked in your exams. And on your exam, they keep these three things in mind, which I think is important. So like we say, when what you have a glass rod, glass rod, the way it is being called, rubbed with silk, the charge produced is called what? A positive charge. That's the first one. So positive charge is produced as a result of rubbing or the material that is used to rub. I hope I am communicating. The second point I need something like a napkin. My hand is very wet. The second one is ebonite. We have ebonite rod rubbed with four. We give you a negative charge. Quick concept, that is what we are doing. And the third one, polythene, which is polymerization of ethene, rubbed with duster. Rub with duster, thank you very much. Now, rub with duster will give you a positive charge. Please just keep that at the back of your mind. Polythene rub with duster will give you a positive charge. I don't know why my hand is bringing out water. With duster, we give a positive charge. So, in as much you keep this in mind, the aspect of production of charges is very simple. And again, you can also keep the basic knowledge, which I think is one of the fundamentals of this topic. Benjamin Franklin, which says, experiment, which says, like poles repel, unlike poles attract. I think that is basic. Like poles repel, then the unlike poles attract. So now, in this question, we can now use the fundamental knowledge which I have tried to explain from what? From producing what? Electrostatic charges. We are talking about charges, electric charge. In fact, when we talk about charges, we said the charge on a body is defined in two ways. Please keep it in mind. Another important concept, quick concept, which I think you need to always keep in mind. Now, we say charge can be quantized and it's given as Q is equals to NE. Very important. Q equals to NE. Let me write the E in small letter. So Q is equals to, is proportional, what is the number of electron, where N is the numbers of electron, the product of the numbers of electron that is flowing. So we define charge in terms of electron. N here is a set of integer, is a set of integer. Don't worry about this because all these are just something some question can ask you. Calculate the total number of charge if the electron, if there are 50 electrons flowing and the charge of an electron is given. You guys know that from your chemistry, 1.6 times 10 to the power negative 19 coulomb. RA milligram. Chemistry. I hope you still remember that. So if you want, 500 electron multiplied by the charge. This is a quick formula you can always use to calculate the total amount of charge that is flowing in a particular in a sphere, because we use all those sphere when we talk about a uniform shape. Now, for now, I'm not going to talk too much of details. I'm going to give you what is needed exactly to actually answer a question. And I wouldn't talk around it because I can also tell you what can be asked with respect to what you have here. So from here, I think this is direct and very simple to do now. And because it is simple to do, what we do here, guys, is just to know that you can now define charges, what I want to say here, in terms of two things. For example, in terms of electron, we now define positive charge as positive means deficit of electron. All these are concepts, deficits of electron. You can watch mostly academic concept, full concept video, but this is also quickly going to map out what you need to know. This is just a revision strategy. That is the essence of all this physics chapter, to make you actually pass and score and get a very high score in your forthcoming physics examination. So positive means deficit of electron, whereby that is positive charge. You understand that. A negative charge means negative charge means excess of electron. So now you can also define in terms of proton, it will just be opposite of this. Positive means excess of proton, and what negative means deficit of proton. So careful, electron is negatively charged, and that is why when you have negative charge, it means excess of electron. I hope you understand. So charges are quantized. Always keep that at the back of your mind. So back to question, to answer this question, because time is always a major constraint. This is 1 after 5. I'm recording this video 1 minute after 5. I'm giving 47 minutes to do this. I hope I can do the 15 questions in 47 minutes. An ebonite rod rubbed with 4 and attract a glass rod with 6. What is the charge of an ebonite rod that is rubbed with 4? It produces a negative charge. Then it will attract a glass rod. When a glass is rubbed with silk cloth, it's definitely going to give you a positive charge. So negative and positive are what? Are unlike poles. From Benjamin Franklin. Unlike poles will definitely what? Attract. So the reason why they attract is because one has positive and the other has negative. So simple. Ebonite has negative and what? Glass has positive. So answer to that is straightforward and direct. We pick this as our question answer. Please. Yes, student, please. Now, the next one, in the process of electrification by induction, the amount of induced charge in relation to the inducing charge is the dash. Now, let us understand a very quick concept, very quick concept. What you learn in classroom for 3.5 weeks will be taken in Mosey Academy in just 1 hour. Let me even say 45 minutes. Now, when you talk about transfer of charges, like I said, we have method of contact. That is, a charged body will bring in contact with an uncharged body. Another method we use is method of friction. I just explained friction. That is rubbing. When you rub a body, you guys have talked about that. You rub your pyro, where you rub it on your head and you bring it very close to a piece of paper. It's going to lift that piece of paper because of what? Static charges. Electrostatic. That is the definition. Then the last one I want to talk about here, which is what this question asks you, is the method of induction. Let it be known that induction is just a simple method of charging a body without touching it. That is the definition your teacher will give you in junior classes. Fine. Now, every system of body, so everybody now, that's when I say everybody, I don't mean every individual. Every system of body, every body, every state of body definitely has positive and negative charge. Now, but what we know is that when we have a uniform sphere, a metallic sphere, please listen. Now, if we are actually saying the positive charge are distributed outside the metallic sphere, now it doesn't mean that this sphere is not having a negative charge in it. Let me just start from that. You need to understand. So, but the negative charge are now inside. It's like your potentials, which you never show. You understand? They are in you. So, but the charge that are distributed outside the sphere, I'll still talk about distribution of charges, which is one of the most important topic under electric charge, because here we focus on electric charge and electric field. The next will be capacitors and stuff like that. Now, keep it in mind, you have to understand that in method of induction, we always produce, for example, I can have two bodies that are in contact. As I bring a charged body very close to that body, let's say this is a earth, now which is positively charged. There are two bodies that are in contact, just for illustration's sake. Now we say this body close to it, we induce a charge of this, whereby the one that is next to it will induce opposite charge. That is just the simplest way. But the question is, how is that possible? What I always tell students is this. Now, always know that a body, like I said, has the characteristics of both positive and what? Negative charge. That is how the body looks like. So now, when you now bring what? A positive charge close to it, it will definitely what? Take that positive, because positive is the one dominating now, which will be the first one that will be distributed on the first one, on the first sphere that is close to the rod. Now, the other charge that is at the other side of will now be distributed to the one that is very close to it. That is the simplest way you can always think about induction method. So it's just a process of charging. The first thing is bring them in contact. When they are in contact, the next thing is what? You are going to actually distribute charges. Without touching it, we say by earthing. That is the process we call it, earthing. Earthing. So by earthing, the charges are going to be distributed, and they are going to have what? They are going to have what? Opposite sign. You can see that the sign are not equal now. The induction always give you opposite sign, please small, opposite sign of equal magnitude. Equal magnitude. I short magnitude as MAG. So always keep it in mind that if you are charging by induction, the signs are not going to be the same. Like I told you, each body has a tendency of both positive and negative. If what negative is being negative will take over, then the positive will move to the other one that is in contact. And the last point is you just separate. This is the method we use. Sorry guys, a quick concept, quick way to understand, and quick way to pick right answer. So now, same sign, never. Same in sign but greater, no. Opposite in sign but no. I said same sign, opposite sign of equal magnitude. It will distribute with respect to the body that is what? That is producing the charge. So always keep that. Opposite sign but less. Less, it's not greater, but it is equal. Opposite sign, opposite in sign, and equal. So this is the right answer to this one, guys. That is the second question of the day. I have used 6 minutes because I am explaining concept. Please, most the academy team with my new calculator, please bring it very close. Now, the next is what is the correct sequence of the steps for charging an insulated conductor by induction? Very good question. That's a good one from those that set this. I love this. Now, we'll just talk about induction method. Now, the first process is bringing a charged body near the conductor. Just like what is here. I love this. In fact, these two questions that I'm going to answer, we are going to be like answering it at the same time, simultaneously. So answering this simultaneously, we can say that if we want to answer this simultaneously, you can say the first thing is what you are going to bring that body, that particular rod or whatever. You are going to what? Bring the conductor near the what? The charge body. Bring the charge body near the conductor. The body you want to charge, you bring it near the conductor. That's the first step. Roman figure 1 is correct. Absolutely. Now the next one says removing the charge body. No, removing is going to be the last process. Please listen. Removing is going to be the last process. Why? Because it is after the charges has been distributed. When this now is now placed in contact with it, like I said, each of these body has negative and positive. Because the charge on the rod is negative, negative will take over this in this case now. So after doing that, you now touch it, touching but with your finger, so that the charges is going to be distributed. That process is called earthing. Please note that I've talked about it now, so I don't need to waste time on the same thing because I'm repeating myself. So the next process step should be this one. Then after that, remove your finger after the charges are distributed. I told you this first sphere is having negative and positive by the side. But because this will immediately you touch, the negative side will take over here. The positives will now what be distributed to the other side. It is just a very simple way. And I told you when you want to do this type of thing, always keep it in mind. One body must be a conducting body, in which what it will conduct. So always keep that at the back of your mind. Then the last process is always when you remove your finger is next. Then after doing that, what do? You separate the body in contact. So always follow this step. What I mean is what Roman figure 1 is the first step. The last step is removing your what? The charge body. That's the last step. The next is Roman figure 3. You touch it. When you touch it, you remove your hand. You are touching it not directly. So note that then after removing your hand, you remove the charge body. So this is the process, which I think, and the last is Roman figure 2. So follow this sequence, and I think you just need to check the one that follow this. I don't think the answer is there, but this is the correct answer. Or maybe I'm the one that cannot see. I'm becoming old nowadays. Okay, choice B. Okay, B is correct. Thank you, guys. Now, the next one, the next question. Let's see this. We have answered this because we've done it. Look at the question. X and Y are uncharged conductor in contact on an insulating stand. A positive charge rod is then brought close to X and Y as shown in this diagram. If X and Y are separated, that is the last way. You can say removing the charge body is always the last process by electrification by induction. Then the rod is held near them. Both X and Y we know X will be negative, Y will be positive. So both X and Y no, X will be negative and Y positively charged. X will be negative. So the answer is X will be negative and Y is unknown. The answer is this. Because we have done that from my explanation, I don't think we need to waste time. I think we are now moving at high speed, not like the speed of light, but the way we are supposed to move. Now, the next is just popular question. Most of the academic team can answer this question without any time wasting. Now, just talking about distribution of charge. Now, according to Newton, Newton is a genius. You know him very well. He's very brilliant at his time, and there is what we call distribution of charge. Now, for an hollow sphere, the way you and your teacher might have explained to you in your tutorial centers, for an hollow sphere, when you talk about hollow sphere, let it be no, I don't want to be drawing, and but I still have to draw. Now they will tell me I'm wasting time. Now, if you have an hollow sphere like this, now what we call hollow sphere, we are calling that you can see that the shape is evenly what it is evenly distributed. You can see it has what a uniform radius. The radius is the same. I will explain it to you in such a way that you can also explain to your friend. Now, because the radius are evenly distributed, now the concentration of charges. The concentration of charge. Another thing you can keep in mind, actually, when I'm teaching, a lot of things will be coming to my head, is that to actually know where the concentration of charge lies, we use an instrument called a proof plane. A proof plane is an instrument that is used to what detect where the concentration of charge lies most. Where the charge is fully concentrated. So for a uniformly charged body or a uniformly charged sphere, the concentration of charge is always what? Outside the sphere. They are distributed evenly outside the sphere. And the reason is because their radius of curvature is uniform. You know, distance from the center to any part of the circumference is the radius. At any point in time, they have equal radius or radii, as the case may be. Now, for a randomly shaped body, you can see their radius of curvature is not the same. If I take this one at the center, distance from here to here is not the same thing as distance from here to here. In fact, in A levels class for A levels student, we say the charge density is inversely proportional to the square of the radius. This is the way we interpret. But for you, you don't need to know this one for now because we might be looking at what is charge density. It is just the ratio of charge per unit area. I told you most academic physics has covered all physics syllabus for high school and for college students. So if you are an high school student, you watch the high school version. If you are a college student, you watch the college version. And hopefully we are also trying to use the new technology to give you the best of the best visualization and as well as experiment for the experiment time question. So guys, let's move on. That is not what I'm here to do. I'm here to provide solutions to questions before me. And I'm doing that with respect to what I have. So because here in this type of a randomly shape or randomly mapped shape, the concentration of that is always lying at the sharpest point. So always keep that in mind. That is what your teacher will tell you in junior class, which is good, very correct. Sharpest point is always at the sharpest point. Sharpest point of what? A random shape. Random shape. So the charge lies at the sharpest point. So the concentration of charge will lie at this point that was labeled E here. And the answer to the question is what? E. Even though the what was the academic team refused to put A, B, C, or E in the question, but the answer to this is what? Option A can be B, option B can be C. Hope you understand what I'm saying. Option C can be A. They want you to work with respect to what is here. So E is correct. You keep that at the back of your mind, and that is that. Another thing you can talk about when we get there, don't let me start talking because of time. We move. Now, the next is which of the following items can be used to compare the relative magnitude of electric charge of two bodies? When we talk about magnitude of charges, listen, magnitude of charges. For magnitude of charges, we use the gold leaf electroscope. You have studied in your junior classes. A gold leaf electroscope is used to calculate the magnitude. You can use it to test electroscope. You can use it to test and to detect the magnitude of charges. So now, how do you use it to test for charge? It is made of a gold leaf and a metal cap. And it works as a result of what? The simple principle of Benjamin Franklin. Like poles will always repel, unlike pole will always attract. You have learned the method of what? Electrification by induction. Every system, every bodies actually have what? Two charge on them. The thing is what? They will always induce an opposite charge whenever the charge, that is what? So always keep it in mind. Sorry about that. Apologies. Now, whenever a rod or a particular charge body, a conductor is brought near the what? An insulator, there will be a distribution of charge. We've talked about that. So the leaf is always made of gold or aluminum because you need something that can easily what? That can easily diverge and converge. So aluminum can also be used as the leaf of a gold leaf electroscope. In your junior classes, you all know how it looks like, how a gold leaf electroscope looks like. And if you don't know, you can watch the gold leaf. Sorry about that. You can watch. You can see they're asking me not to draw because of time. Why won't I draw? I will draw. Nobody can stop me from not drawing. Oh wow, see, that is what you get if you are using strong head. So I'm not drawing again then. So now the answer to this is so simple because I've explained it. Now, see, this is used to secure what? To compare the magnitude of charges. Always keep that in mind. This is the answer to the question. This I told you it is used to what? To actually know the concentration of charge. This one is used to secure large amount of charges. Secure large amount. I will teach you everything of similar charges. In fact, for A-level students, we'll talk about what we call a Van der Graaf generator and how it works. Lighting conductor, which is also part of elementary stuff, which I believe you can watch that. And if question asks me to explain to you, I'll definitely do that because I'm working with respect to the new pattern of question. So that's the answer to that. Gold leaf electroscope is correct. We move to the next slide. I think the questions are being arranged from what's simple to tough. And I love this method. Kudos to those that are arranging this for us. Thank you and God bless you. Aluminium is sometimes used as the leaf of an electroscope. I just talked about this. Do I need to still talk about more concepts? Okay, they said no. Now, it's a light material. It's a good conductor. It's not answer. It's a good insulator. It's not can be converted into thin sheets. This is the right answer because it is very light. Now you can think about it is light because it is light. It can be no. It can be converted into thin sheets. When you convert aluminum to thin sheets, then it can be used as a foil of of the gold leaf. So note that it is not because it is light, but because it's aluminum is what can be converted into what to thin sheets so that it can what deflect easily. I'll just write that for you now. It deflects what easily. So that's the right answer to that question. Choice D is very correct. You keep that at the back of your mind. So guys, I'm almost there. I am keeping people are waiting for me, so I need to increase my pace. Apologies for that. Apologies. A negatively charged rod is brought near the cap of a gold leaf electroscope. See, the rod, the charge, the polarity of the charge is negative charge. Also note that what when we talk about charges, when we talk about distribution of charge, see, when we talk about charges, when we say arrow facing up, we are talking about positive charge. Ah, look at my hand, God, because I'm rushing. Positive charge. Because another thing you need to know position. Then whenever you have the direction of arrow that is pointing down, the charge you are talking about is what? A negative what? A negative charge. That's also very important because of diagram of what on charges. Charges are scalar quantity. Please note that. Fields are vector quantity. Another important thing. Fields, either electric field or When we see question on fluid, I'll talk about fluid. A negatively charged rod is brought near the good leaf. The cap earthly momentarily, the cap earthly momentarily. It's not momentarity. While the rod is near to it, the rod is then removed. Which of the following is dash? Now we don't need to waste time. I've talked about that. Since a negatively charged of the rod is what is brought now in the electroscope. What happened to the cap? The cap is the head. I don't want to be drawing. See, the cap will induce what a positive charge. We've talked about that by method of induction. So now because it is being earthed, so when you earth something means it has been touched. I told you the other time. So that is indoor induction. So induction means it will distribute the opposite what charge. This is a negative charge. This is going to distribute the positive charge. So when positive charge is now at the cap, now why is it positive charge? Because it was earthed. Earthed means electrification by induction. So this is negative. So induction would make you know that this will be what positive. And you know how a gold leaf look like. I am not supposed to draw, but if you don't know how a gold leaf actually look at my diagram. God will help me today. Only God will help me. Just for illustration's sake, anyway. Nothing more pretentious. Yeah. I want to color this thing because it must be. The thing is, I am supposed to use my ruler to make my hands straight. But all the same, it is not what is important for now. What is important for now is that there is a leaf. And you must know that what the leaf is always made of gold and aluminum. That is the most important thing for now. I hope you understand. So just this is not a good diagram. Oh. You are drawing this one for your teacher as a wife student, your teacher will slap your face. Just telling you that you draw a better diagram. But what matters is you can see the cap here is what is positive charge. Now look at this. The rod is then removed. When it's removed, what happens? There will be distribution of the charge. So the positive charge that is on top of the cap will now be distributed to what? To the what? To the leaf here. So the leaf too will what? Will now be what? Positively charged. So that is what you just need to know in this type of question. So let's pick the correct answer. The cap will be positive charge and the negative charge leaves and the leaf will be negative. It's a rubbish. Now again, you can see the same polarity. What happened to same polarity? Like poles what? Repel. Like poles repel. So when we say they repel, we say there is an increase in divergence. That's in the leaf diverge. I'm trying to gesticulate now. You can't see me. Increase in divergence. Don't worry, very soon you'll be seeing me. My new machine is on the way. It's coming. Very soon you're gonna be seeing me, and you are going to see me. I know what I'm saying. Now, the second one said the cap will be negatively charged, and this is rubbish. I've told you this is positive and this is positive. It also the cap and the leaf will be this is the right answer. Do I need to read any other option? Because of time, let's save the time for people that are waiting for me. So, guys, understand the concept very well. Whenever you add something, it means induction. Whenever you earth, touching with the tip of your finger, that is induction. Induction always gives opposite charge to the initial charge on the rod. That is the logic. I hope you understand. Don't tell them I've told you the shortcut. That is the way to get the answer. So the next one, the next question, very good. Oh wow, electroscope. Was the academy team electroscope? Well done. What happens when a positive charge insulator is placed near the disc of a positively charged gold leaf electroscope and is then removed? This is a simple question. Should I leave it for you to do? I should solve it. I should solve it for you guys. Okay. I will solve it. Now, look at the polarity. Positive. Look at the electroscope. Positive. Like poles. What happened to like poles? Like poles repel. Like poles repels. Now, when like pole repels, that means what? It will rise further. So the leaves will not fall. The leaves will rise further and remain in that position when the body is removed. Now, look at this. The leaves falls is very wrong. The leaves rise further and fall to its original position when the body is removed. Yeah, you can hold on that. The leaf falls is out of it. Nothing happened is out of it. Now, this is the true question because I know students very well. Look at this. The leaves rises further, fine, we already know, and remain in that position when the body is removed. When the body is removed, it will what? And falls to its original position when the body is removed. We are talking about divergence now. When the body is there, you understand, the positive charge is distributed to the leaf. The moment the body is removed, you know what it means. The charges will be going down. They will be what reducing. And when they are reducing, what happens? The leaves go back to where they were at the initial position. Forget, permit my English. I'm not your grammar teacher. So that's that. The leaf rises further and remains in that position. It can never. How will it remain there when the charge has stopped flowing? So please note that. So the question answer is choice B. And I think it's a simple question for you guys, but I know some students still have issues in picking right answer when they were able to conquer some wrong answers. Then they see two similar answers, they always They always still fall a victim of wrong answer. So guys, still on electric charge, I think the question was well arranged. I love this. Which of the following field pattern between two unlike charges is correct? What do we say? What do we know about unlike charges? They attract. Unlike charge. Unlike charge what? Attract. Thank you very much. You guys are doing wonderfully well. Because they attract, always know charges flows from positive to negative. So if there is positive now, it will flow from something like there's what we call feed lines. That is the lines we use to represent electric field. Feed lines. They are lines used to represent electric field. They are imaginary. Imaginary. Important. These are their characteristics. Imaginary. I cannot even spell imaginary again. I hope it is correct. Sorry about that. I can't spell for now. If it is not correct, write the correct spelling. Imaginaries. They are imaginary. Another thing about them is what? They never cross each other. I'm talking characteristics of field lines. Never cross each other. Never cross each other. Basic concept. Never cross each other. They are used to what? They are used to represent field. Used to represent. Rep means represent fields. And see what I'm doing? And then is what the last one is what they travel from what? Positive to negative. Travels from, that is why they can never cross each other. From positive, concept video available, to negative. To neg. Neg means negative. Guys, we are rushing, permit me. So when you say two unlike poles, expect them to move. I told you about positive. How do I tell you? What do I tell you about positive? How do I say they face? The arrow is going face up, right? So this is positive charge, my dear students. Positive charge shows excess of proton, deficit of electron, right? So they always the arrow is always pointing up. Basic and short concept. So this is positive charge. So if electric field lines travel from positive to negative, the pattern is going to be like hemispherical time. You can see, we say they move. Now I can't see this diagram very well, but I can see the arrow. The arrow will help me. So positive to negative means, the direction of positive is, now you can see up. Now if it is now moving in an hemispherical pattern like this, see, when I say hemispherical pattern, forming something like an hemisphere. I hope you know hemisphere in your maths knowledge. For those of you, everybody should know what. So it will be like this. So the field lines are imaginary. This thing I'm drawing are not real because I'm rushing. I should have used a, what's it called? My ruler to draw. So now they will definitely draw from positive. Look at positive is arrow facing this side. So now it should be pointing outside. I hope you understand true what? Negative. Negative is arrow facing inside. So the hemispherical time move from positive charge to negative. So you don't pick arrow that is like, look at this arrow is wrong. This arrow is wrong. I don't know. This one is not clear enough. But what I need to know is that this side must be positive. This side must be negative. That's the only thing. So that's what you are going to, because this is not clear enough. With the academic team, next time you are drawing, please draw something. This is other side of arrow is also wrong. So these two are pointing towards the side I told you. And because they are pointing towards those side, any of these two can be correct. But the only difference that will be there is that this one should be plus and minus. And one will be minus and plus. So the one that is plus and minus will be what you are going to pick as your answer. So hemispherical in shape, when two unlike poles are being drawn. The field pattern is always hemispherical in shape. If they are like poles, they are not going to be hemispherical. They are going to form something like triangular hyperbola, something like that. It's not something you don't know. It's what you have seen before. For some of you now, I know what you are thinking that how will I know this thing? You can know it. We say you cannot know it. They found something like this. I know you have seen something like this, shape like this. So all these things are just my hand is not straight. So I mean my hand. My hand is not straight for now. So I'm just trying to let you see. Please cancel. Please bring color blue back. Thank you. Please, I need blue. Thank you very much. So this is it. So it should be a normal diagram. So if they are similar, this is the type of shape you expect. I'm only giving you a perception of what you expect, as in just visualize it. For when I get to magnetic field, I will draw a lot of field pattern for you. So for now, I limit it to just what I have in front of me, which is in terms of electric charge. This is 29 after plus the remaining 10. Now, the calculation part, that is electric field. Now, before I start the calculation part of the electric field, you will need to understand that the definition of electric field is given as the point. Electric field is a vector quantity. We've talked about that. It is a force acting perpendicularly per unit positive charge. First point. Now, force acting perpendicularly per unit positive charge, F by Q. Measure in Newton per coulomb. F is N, charge is coulomb, Newton per coulomb. Electric field is also defined as the what? Potential per unit distance. Potential different, PD, volt. Potential per unit distance. Potential is PD, so it can also be volts per meter. Keep it in mind, very important. Now, another important thing, I'm sorry I have to rush you now, is Coulomb law of electrostatic. Now, according to Coulombs, in that year, you don't need the year, nobody will ask me the year, but if you want it, I will tell you. Now, Coulomb gave us his own law, and it said the force is always equals to KQ squared by R. Now, we define K as 1 over 4 pi epsilon naught. So keep that in mind. This is the simple law. He said by R squared. I will have actually screwed that, but I can't screw. When I start solving, I will definitely know there's an error. So this is Coulomb's law. He said force of attraction and repulsion, I'm quoting a language form for Waec students, is inversely proportional to the square of the distance apart and direct proportional to the what? To the product of their what? The product of their charges, which is Q1, Q2. Basically, you say Q1, Q2 over R squared. Okay, then your teacher will now write it in full way that Coulomb's law force is a vector quantity, that's why arrow is on it. It's 1 over 4 pi epsilon naught times what? Q square over R square, because this 1 over 4 pi epsilon naught is always given as a constant. So if you write your formula like this, my dear students, you are right. So this is Coulomb's law. This is its formula. There are limitations to it. The two limitations you can be asked in the new pattern of UTME. The limitation to Coulomb's law is 1. It only works for what? Point charges. Point charges. When I say point charges, small, shorty charges, point charges. And the second limitation for Coulomb law is what? Charges must be at rest. Charges must be at rest. Write it down because it's important for some questions that are not numerical. I will ask you just what? To actually what? Which of the following is an assumption from the limitation? Then again, we call this one epsilon naught. Now we now define that in terms of electric field as E is equals to, we say E equals to epsilon naught times what? Permittivity, like this. Now, or basically, we define in terms of the way your teacher will define for you in junior classes. So let me scatter your head now. Is that you define the relative what? You now define what we call what? You know, we call this one epsilon naught. You now define what we call dielectric. So we say the dielectric, relative dielectric is permittivity in the medium divided by the one in what? In vacuum. So this is the definition we define for relative permittivity, which is in terms of what? In terms of what? The epsilon naught. So whenever you are looking for the relative, it's always the medium divided by the vacuum. So basically what I want to write for you before was like the epsilon m, em is equals to er times what? E naught. So free space is called vacuum. So but it's better in this way I've written. Write it down because it's also important in some question that we ask for relative dielectric. So we define dielectric when the body is taken from one point to another, it's moving from a vacuum, which is free space, to a particular medium. So these are things you need to keep in mind. But for your own level, we are only going to talk about is what? A uniform sphere. But for advanced level student, we talk about what we call what? Extended bodies. Now, concepts are available amongst the academy for those of you that you like to know everything, you cannot actually check them out. So I think this is enough for you to answer this simple question. Then always note, we said it is applicable for point charges. So because it is applicable for point charges, you are going to understand that what the charges are measured in coulombs. So we now reduce them to the simplest of the simplest coulombs. So we now have the conversion scale. The first thing we need to understand is that we have what we call what? What we call microcoulombs. They are measured in terms of microcoulombs, which means 10 to the power negative 6 coulombs. They are measured in terms of nanocoulombs, which is 10 to the power negative 9 coulombs. They are measured in picocoulombs, which is 10 to the power negative 12 coulombs. This is what they will not tell you, but I will tell you because I love you guys and I want you guys to pass. So this is the way you expect to do it. So direct relationship now from the formula, electrostatic force is 1 over 4 pi epsilon naught times Q squared by R squared. Directly, Q square means Q1 times Q2. So because there are different charges on this plate. Now let's write. Now directly you can say F is a vector quantity, it's not needed, you don't need to write it. 1 over C in the what? 1 over 4 pi absolute naught is given. So 1 over 4 pi absolute naught is time 9 times 10 to the power 9. Copycat times Q is the first key is look at this microcoulomb. 5 times 10 is per minus 6. I just tell you about micro now. 1 microcoulomb, 1 nanocoulomb, 1 picocoulombs times 8 times 10 is per negative 6. Everything here is divided by square of the distance is 0.02 whole square. I hope students understand. So that is how to do that. If you do this very well, just use your calculator to finish this stuff. And if you are able to conquer this should give you, I'm sorry, I'm very, very fast because this will give me 0.004. When I square this one, 0.00 is 4 times 10 to the negative 3, 4 here, 1, 4 here, 2. Look at the way I'm doing it. Use your calculator on the screen. It is allowed. Apologies, I am rushing. Apologies, I am rushing. I have fishes to fry. That is why. Now, in this case now, if I do this, it's 0.04, 0.02 squared, 0.04, 004. As 4 times 10 to the minus 3. When minus 3 comes, it will be plus. Minus 6 plus 3 is minus 3. 4 here, 1, 4 here, 2. 5 times 2 is 10. This is 90. That is 9 times 10 is power 2. You can see the way I have solved without calculator. Though you are going to reach, in fact, you are going to do more than that if you can actually get serious now and listen to all these guidelines. It's very simple to do all these things without calculator. And you are not so good in in all those type of manner. Try as much as well and do it one by one, the way you are used to. 9 times 5 times 8. Then there's 9 times what? You can see indices plus. That's 9 minus 6 minus 6 minus 12. 9 minus 12. Do it one by one. If you do it well, you are going to have 9 times 10 to the power 2 Newton. My answer was 900, which I convert to 9 times 10 to the power 2 Newton. So that is a simple question. It's because of time, my dear students. Apologies as always. I am not like that. The next, guys, is this one. Now, the question is a two parallel plate at a distance of 8.0 times 10 to the power negative 3 apart. The distance apart is d. 8 times 10 raised to the power negative 3. Please, 8 is same thing as 8.0 meter. That is the distance. Please, most the academic team. Now, I don't need you guys, but I just want to watch. Now, as a PD, what's PD? V is PD. Potential difference. That's 600 volts. That is what you have with a negatively plate that is at it. What is the electric field? So electric field is always volts per unit distance. So it starts with what we have here, V over D. My dear student, what is V here? 600 divided by what is D? 8 times 10 to the power of 3 minus 3. On simplification, see, 600 is 6 times 10 to the power 2. I can now say 6 over 8. Look at the meaning, guys. 2 can go in 6 3 times. 2 can go in 8. That is 4 times. 3 over 4 is 0.75. This one comes up. So I'm having 75,000. Please confirm my answer. I am a kind of person that I am human like you guys. I can make mistake. Human, I can make mistake. Volts per distance is VM. Either VM or Newton per coulomb or volts per meter. You are still talking about the strength of an electric field. Electric field also has a property. It can actually what? It can actually what? It's a kind of property that we said it is defined in terms of what the amount of force per unit positive charge. So electric field can exert force. It's exact force. Write it down. It's exact force. Because of non-numerical question on stationary charge. It's exact force on stationary charge. In fact, that is one of the most simplest thing that differentiates electric field from magnetic field. Electric field exert force on stationary charge. Magnetic field don't exert force from stationary. I think this is right. Please confirm my answer. If it is wrong, you can always put comment under you can always write the right answer under the comment section, guys. Then we go to the next page. Almost there. I think this is the last page. Hopefully it will be okay. That is the last page. Last two set of questions. Yes. A charge of 1 microcoulomb, I am reading, is moved through a distance of 0.1 meter against a uniform electric field of strength E. If 20 joules of work is done in the process, calculate the magnitude of the electric field, I guess. I don't know. Now, the question says there is a charge. I will just write parameter because the question is incomplete. But all the same, we can still do it. 1 times 10 raised to power minus 6. I hope you understand, which is same as 10 raised to power minus 6. I have only converted charge to coulombs, from microcoulombs. Distance R. I'm using R as distance since we started this section, 0.1 meter. It's moving in using my magnetic of strength E. If work done is 20 joules. Calculate the magnitude of E. We are looking for E. E equals to this. Now let it be known that you can also write E in terms of say E equals to F over Q. Remember? I will say F is equals to, I just want to talk about it because it's important, KQ squared by R squared. If you substitute, you can see that 1Q will get cancelled. So you can say E equals to KQ by R squared. So please note that. Another way to write E. E is equals to KQ by R squared. It's very important. Where K is 1 over 4 pi epsilon. And you can also define electric field potential V as KQ by R. How do I come about the electric field is V over R, V over R. We are looking for V. Now, E is this now. Then, 1R will get cancelled out. So these are three formulas that you need. This, and this. This is electric field potential, electric field intensity, electrostatic force. All these three formulas are very important. So now you've learned from early classes that work done is equal to force times distance. I'm taking distance in this concept to be hard. So keep that at the back of your mind. So the work done is this. So we define this. Now, electric field potential is defined as the work done in moving a particular charge from a point in the charge to infinity, from infinity to a point in an electric field. Let me also mention something about electric field. If you have a uniform shape, the electric field inside a uniform shape is always zero. So calculation will ask you to calculate electric field for a uniform shape. You don't need to do calculation. It will give you parameters, but the electric field is still zero. New pattern of question. Keep it in mind. It is only random shape that has electric field. Please note that, and that is what we are trying to talk about. For there, we are looking for the magnitude of electric field. To get that, my dear students, we know the charge. If you want to go by this, you just have to follow the same process that we have talked about. Electric field is volts per unit distance. That's V over D. Now the work done in moving a particular charge from infinity to a point inside the electric field is called electric potential. So the work done, I can use this one as my work done and use 20 directly. For those of you that you don't know, and for somebody that wants to use V over R to get your distance, this is what you do. You can see the distance moved by the charge. So what you just need to understand here is that to solve this type of question, you still need to use your words. If you say E equals to V over R, you need to get V. You can see you need to get the value of V. So from V, you can say KQ by R. So you substitute your Q, you substitute your distance. K is 9 times 10 by 9. Then when you get the answer, divide it again by what? By this. But another person will say, what about this? I can do it in another way in terms of force. If I want to do it in terms of force, what is work done? The work done is 20. I want to show you another way. Force times what is the distance? The distance is 0.1. So now make F to a formula. F equals to 20 divided by 0.1. 20 divided by 1 over 10. 20 times 0.1. That's 200. Please confirm that 200 Newton is a force. 20 divided by 0.1 should be 200. Please. So that force on the work, if the amount of force required for this work is this, then you want to calculate the magnitude of electric charge. You will now use this formula. That electric charge E is equals to F over Q. I hope you understand. What is F now? F is 200, right? Divided by the charge. The charge here is you can see the charge 10 raised to the minus 6. I hope you understand how I come about this. I just converted. So you say 2 times 10 raised to the minus 2 times 10 raised to the 2 over 10 raised to the minus 6. Another person can say it's just 2 times 10 raised to the 2 plus 6. That's 2 times 10 raised to the 8, which is the answer and which is correct. So that's the answer. Volts per meter. Option A is correct for this question. But I can also do it like this. I'll also get the same. So guys, like I can use electric field is volts V over R. or electric field is what's it called? Is also equals to force by nature, which is what I use. So anyone you are using, you have your answer. So the last question for this set, my dear student, is calculate the electric potential at a distance of 20 centimeters. Don't forget to convert from a point, which is this, place in air permittivity of epsilon naught is 1 over 4 pi. This is this. Now, what is potential? Look at this. I told you V is equals to what? KQ by R. What is K? K is what? 1 over 4 pi. This is the last question, sorry. Epsilon naught, which is 9 times 10 raised to power 9. So let's just use the formula. You can write it like this in this format. V equals to 1 over 4 pi. K is this times Q over R, which is the simplest form. So substitute the parameter. What is 1 over 4 pi epsilon naught given? 9 times 10 raised to power 9 multiplied by what is Q? Charge is 0.015. Divide your answer by R. What is R? Convert 20.0 centimeter to meter. How do you convert from centimeter to meter? Divide by 100. 20 divided by 100 should be 0.2 meter. So all what you just need is to press all these variances. So and you can, if you don't want to press, you can also convert this something as 15 times 10 raised to power 1.5 times 10 power minus 2. So then please punch this on calculator. Let's just do everything. If you punch this on calculator, I don't have anything to do. Please punch. I'm waiting for your response. 9 times 10 raised to power 9. 9 times 10 raised to power 9 multiply by, I'm asking my students that are here to work me punch. I told you they are here, they are laughing because they've done all this stuff. Then multiply by 0.015. Divide your answer by 0.2. I can actually do it with that calculator. The answer is giving us 675, then 1, 2, 3, 4, 5, 0. So 6.75 times 10 to the power 8. Is that what you have? Must the academy to be fast? 6.75 times after the 6, count the number of data. So that is 6.75 times 10 to the power 8 times 10 to the power 8 volts, which is the right answer to this question, guys. The answer is this, and that is where we are going to be stopping for this section. Guys, I hope you enjoyed this section. See you guys soon in the next part of electrostatic, which is capacitance and dielectric. So under that, we talk about capacitor and the dielectric and different type of capacitor. See you tomorrow, guys. Don't forget to like and subscribe to the channel. Invite your friend also to do so. Bye for now.